Hello friends, here is Mr. Ramesh Chandra, did BTech from IIT Kanpur and taking 5th lecture on complex numbers. Let's learn about the modulus of a complex number and what is the meaning of it and how it works. Let's say a complex number z is a plus iota b. Then we define mod z of a complex number is under root of a square plus b square. Let's have an example. Z1 is 3 plus 4 iota. Then we define mod Z1 as equal to under root of 3 square plus 4 square. That is under root of 9 plus 16, that is 25. So this is 5. Let's have another complex number. Z2 is minus 3 plus 4 iota. Then mod of Z2 will be under root of minus 3 whole square plus 4 square, and that is again the 5 value. There is some basic property of modulus, like if we have z is equal to z1 into z2 into z3, then modulus of z is written as modulus of z1 into z2 into z3, that is mod of z1 into mod of z2 into mod of z3. Like if we have a complex number z to the power n, that imply z into z up to n times. So if we put mod over here, then this mod will distribute it in this way, that is mod z into mod z into mod z up to n times. So this is mod z to the power n. Now how is it helping us? Like if we need to find the modulus of 6 minus 8 iota to power 50 to the whole mod. So what we do is we just take 6 minus 8 iota mod and take power 50, and that is if you think about this, this is equal to under root of 6 square plus minus 8 square, or 8 square is same, so this is 8 square and whole power is 50, and this is 100. 36 plus 64 is 100, so under root 100 is 10, so this is equal to 10 to the power 50. There are other property as well. Let's say if we have a complex number z as z1 into z2 upon z3, then we can have mod z is equal to mod of z1 into z2 upon z3, and that is equal to mod of z1 into mod of z2 upon mod of z3. These are the basic property that we need to remember while taking the modulus of a complex number. Now if we have a z, like z is equal to 2 plus 3 iota into 1 minus iota divided by 5 plus 4 iota, and if we need to find the mod of z, then what we will do is we will take mod of 2 plus 3 iota 1 minus iota divided by 5 plus 4 iota whole mod, and this is equal to mod of 2 plus 3 iota into mod of 1 minus iota upon mod of 5 plus 4 iota, and this is gonna be equal to under root, that is 2 square plus 3 square, 9 plus 4 is 13, so under root 13 into under root, you can have 1 square plus 1 square, that is 2 upon under root of 5 square, that is 25, plus 4 square, that is 16. So this is equal to under root of 13 into 2, 26 divided by 25 plus 16, that is 41. So this is 41. So modulus of this complex number is under root 26 upon 41. So this was the basic of taking modulus of a complex number. Let's understand the meaning of a modulus of a complex number. Let's say we have a complex number z as x plus iota y. So x plus iota y, or be specific like z1 as 3 plus 4 iota. So if we represent z1 as, then we will have 3 as a real number and 4 as a imaginary number. So we will have z1 at here, you can see. So z1 is at this place, that is 3 plus 4 iota, or ordered pair 3 comma 4. So this length is 3 and this one is 4. Then if we join this line, and this is, let's say, call this be p vector, p point, then op vector, that is also called the radius vector, then this op length is the magnitude of op vector, and this is the radius vector. And the magnitude of this OP vector is, you can see from here, that is under root 3 square plus 4 square. So for this Z1 is under root 3 square plus 4 square, and this is equal to 5 in this case. And sometimes we also represent this by R. If we have any complex number, let's say z is equal to x plus iota y, then let's say we have this point as, this is x and this is y. So this point P is the z. Then OP vector is OP vector, that is radius vector, is x plus iota y, and its magnitude is equal to under root of x square plus y square. In another word, that is R is equal to mod z, and that is under root of x square plus y square. In another word, we can say that mod z is the distance of point P from the origin. So what we can say, that we can have a point here, mod z is the distance of P from origin, where P is the position of point Z. One more thing you can have, mod x. If we have like mod x is equal to 2, then you will say that x is equal to plus minus 2, and this happen only for x belongs to real. And even you can also say that if x is real, then distance of x from origin is 2, then you will find these 2 points only. Here 2 and minus 2. 2 and minus 2 are the solution. But if we have mod z is equal to 2, that doesn't imply that z is equal to plus minus 2. What does this imply? Mod z is equal to 2. This imply the complex number z which are 2 unit apart from origin. You can see this is the complex number which is 2 unit apart from origin. This is also, this is also, this is also. And mod z is equal to 2. This doesn't imply the only complex number as z is equal to plus minus 2. But there are infinite numbers of points in this Argand plane, as you can see here, which are 2 unit apart from origin, and they all lie on a circle of radius 2 unit. Modulus of z, this is, if this is a point z, then the distance of this point z from origin is denoted by mod of z. Let's talk about argument of a complex number. Let's say we have a z as a complex number as x plus iota y. So you can see this is x and this is y. And the radius vector OP, call this point P, the radius vector OP is making angle theta. Then this angle theta is called argument of z. So argument of z is equal to theta. And you can see that the radius vector OP is making theta with positive real axis. This is positive real axis, and hence this angle theta is known as the argument of z. Even one student can say that this radius vector is also making angle theta plus 2 pi. So you can say that argument of z for the same z is also 2 pi plus theta. Even you can also say that this make two complete rotation like this, and then this is making angle theta. So again you can say that this is 4 pi plus theta. If you rotate it in anti-clockwise direction, then you will see that this is minus 2 pi plus theta. So for a particular complex number z, you have infinite numbers of argument, but they have some common in all of them, that is argument of z is equal to, that is multiple of 2k pi plus theta, and k belongs to any integer. So here you can observe one thing. Argument z is a many-valued function. That is, argument of z is equal to 2n pi plus theta. Let's say we have a complex number z as 1 plus iota root 3. So if we plot this on Argand plane, then you can observe one thing here. We have this is 1 and this is root 3. So this z is equal to 1 plus iota root 3. 1 plus iota root 3. This is the complex number. So what you are observing here, let's say we have this radius vector and this is making angle theta. Then we can have tan theta, that is equal to perpendicular upon base. So this is under root 3 and this is 1 unit. So that is equal to root 3 upon 1. Hence theta is equal to pi by 3 or 60 degree. So you can say that this complex number z is making 60 degree with positive real axis, or in another word you can say that argument of z is equal to pi by 3, or in general you can have 2k pi plus pi by 3 where k belongs to integer. That is the argument of z. So this is the very simple way to find the argument of any complex number. Let's have another example. This time we have z is equal to, let's say, minus root 3 plus iota. So what you will see here, this is, let's say, minus root 3 and this is 1. So this point is representing z. And you can observe this z vector is making this angle with positive real axis. So if we think of this angle beta, then tan beta is equal to, this length is 1 unit and this length is root 3. So 1 upon root 3, and beta is equal to, tan beta equal to 1 upon root 3. This implies beta is equal to pi by 6 or 30 degree angle. So our argument is not beta, our argument is theta in this case. So argument of minus root 3 plus iota, or in another word we can say that argument of z is equal to pi by 6, or you can say that 2n pi plus pi by 6, where n belongs to integer. Let's move on. Principal argument of a complex number. What does it mean? And what is the difference between argument of a complex number and principal argument? Let's say we have argument of z, and here we have principal argument. We also call it as amplitude of z. That is the principal argument and of z. So what is the basic difference between these two? Let's say if we have a complex number, or radius vector of a complex number z is making angle theta, then argument of z can have 2k pi plus theta, where k belongs to integer. Here you can see that for a single complex number there are infinite values for a argument of that complex number. But in the case of principal argument, amplitude of z, that is theta, is always belongs to in between minus pi to pi. Understand this very important and basic difference. And this is the unique value for every complex number. Every complex number has unique value. Let's understand the principal argument in general. So here we are understanding amplitude of z. Let's say this is the Argand plane, positive real axis, and this is imaginary axis. If we have a complex number z here in the first quadrant, then radius vector will be like this and angle will be measured in this way. If we have another complex number in second quadrant, this is second quadrant, then this is the way to measure the principal value of argument of z. This is always measured with positive real axis. Now if we have a complex number in this quadrant, third quadrant, let's say z2, can we consider this as a principal argument? It is no. Since if amplitude of z is theta, then it must lie in between minus pi to pi, and this angle is more than pi. This is more than pi. This angle is pi and plus something, so this is more than pi. So this is not the principal argument. Then how we will measure the principal argument for complex number z2? Then we have to measure the principal argument for this complex number in this way. Let's have another complex number in this quadrant. Then can we measure principal argument in this way? No. And we have to measure the principal argument in this way. So amplitude of complex number z is in between minus pi to pi. Here you can say that if we have a complex number like z is equal to minus 2, then minus 2 vector is here, let's say minus 2, and this is the minus 2 vector is this much, and you can see that this is the theta, that is equal to pi. So amplitude of minus 2 is equal to pi, and we cannot write this as minus pi. Minus pi is excluding here. Let's understand by an example. Let's say we have z is equal to x plus iota y, and if it is in first quadrant, like here, let's say this is x, this is y, then this is the point P in first quadrant, this is angle theta, then amplitude of z is equal to tan inverse mod y upon x in the first quadrant. Let's say if we have a complex number z1s, minus 2 plus 3 iota, then minus 2 plus 3 iota, that is, this is the Z1 complex number, as you can see here. So this is the radius vector of Z1, and this length is equal to 3 unit and this is 2 unit, and call this angle B beta. So tan beta is equal to 3 upon 2. Hence beta can be written as tan inverse 3 by 2. Or even we can have beta can be written as tan inverse mod of 3 upon minus 2. That is again tan inverse 3 by 2. And this is the beta. And you can observe that this is not the principal argument. So to find the principal argument of Z1, we will have amplitude of Z1 as this is beta, hence this angle must be pi minus beta, that is pi minus tan inverse 3 by 2. And what about the complex number is in fourth quadrant? So if we have a complex number in fourth quadrant, and let's say this is the complex number Z in fourth quadrant, then we will measure amplitude in this way. Let's call this be theta. Z is equal to x plus iota y, and you can see that x is positive and y is negative. So tan theta can be written as mod of y upon x. So theta is equal to tan inverse mod y upon x. But for amplitude of z, for amplitude of z, then we have to take minus sign of theta, that is tan inverse mod y upon x minus tan inverse of mod y upon x. In the same way, in this quadrant, if we have a complex number like this, that is z1 is equal to x1 plus iota y1. So you can observe here both are negative in sign, and hence this is mod of y1 and this is mod of x1. So if we think of this angle beta, then tan beta is equal to mod of y1 upon x1. So beta can be written as tan inverse mod of y1 upon x1. But this is not the principal argument. So amplitude of this Z1 can be written as that is, this angle is pi and this is beta. So this is pi minus beta, and since this is measured in anti-clockwise directions, we have to take minus sign for this case, and hence this is beta minus pi. So that is tan inverse mod y1 upon x1 minus pi. So this is the principal argument for a complex number in third quadrant. So here you can observe the clear picture of the principal argument and their calculation. In the first quadrant, principal argument is calculated as tan inverse mod y upon x, and in fourth quadrant it is the negative of this. You can observe here, this is, let's say, z1 vector and this is z2 vector, and if this is theta, then this must be minus theta. In the same way, in second quadrant, the principal argument is calculated as pi minus tan inverse y upon x mod, and in third quadrant, that is the negative of this. So here you can observe minus sign here, or even you can write it as tan inverse mod y upon x minus pi, and that is the negative of this. So you need to remember this figure whenever you are going to calculate principal argument. What you need to do is first observe a complex number in which it is like, let's say if we have z1 as 3 minus 2 iota, then you can observe this lie in fourth quadrant, x is positive, y negative, so this will apply. Let's say we have z2 is equal to minus 3 plus 4 iota, then you can see z2 lie in second quadrant, minus and y is plus. So this is the formula to find the principal argument. Let's have question number 1. Here are few complex number whom we need to find the principal value argument. Let's plot them one by one. This is x, this is y, and first we have a complex number 2. So you can say this is 1, this is 2. So if we have a complex number 2, then you can see here this vector OP vector is 2, and this is making angle 0 with positive real axis. So amplitude of 2 is equal to 0. Now if we have another complex number as 1 plus iota, so this is 1 and 1 more on y-axis, so this is the complex number z1 as 1 plus iota. So you can observe here this is making angle 45 degree and this is in first quadrant, so amplitude of 1 plus iota, that is in first quadrant, so we'll follow the rule tan inverse mod 1 upon 1, that is tan inverse 1, and this is equal to pi by 4. Let's talk about 3 iota. So you will see here this is 1, this is 1, 2 and 3, and 3 iota will lie at this point. So if we plot the position vector 3 iota, then you will see this is 3 iota, and you will observe that this is making angle 90 degree with positive real axis. So amplitude of 3 iota must be equal to pi by 2. Let's say another complex number is minus 1 plus iota root 3. So this is, let's say, minus 1 and this is root 3. So a complex number this will say about the minus 1 plus iota root 3, and this lie in second quadrant. So amplitude of minus 1 plus iota root 3 is equal to you can say this is pi minus tan inverse mod root 3 upon minus 1, and this is pi minus tan inverse root 3, and pi minus tan inverse root 3 is pi by 3, and if you simplify this you will get 2 pi by 3, that is 120 degrees. So if you plot this complex number, complex as a position vector, then this angle will be the principal argument, and this is 2 pi by 3. Let's talk about minus 2. We already discussed for this, that is amplitude of minus 2 is pi. For sixth one, for amplitude of minus 3 minus iota root 3, you can see this lies in third quadrant, so we will follow the rule of third quadrant, that is minus of pi minus tan inverse mod of y upon x, that is minus root 3 upon minus 3, and that is minus of pi minus tan inverse 1 upon root 3, and that is minus pi minus tan inverse 1 upon root 3 is pi by 6. So this is pi minus pi by 6 is 5 pi by 6. So this is minus 5 pi by 6. Let's talk about minus 5 iota. So you will observe from here, let's say this is minus 5. So this is the vector showing the minus 5 iota, and this is the angle that we need to plot. So argument or amplitude of minus 5i, that is equal to minus pi by 2. This is the negative angle pi by 2. And for the sixth one, this is 1 minus iota. This lies in fourth quadrant. So amplitude of 1 minus iota is equal to minus tan inverse mod minus 1 upon 1. That is, y is minus 1 and this is 1. So this is minus tan inverse 1, and that is minus pi by 4. And for principal argument for complex number 0, let's say this is a complex number 0, so amplitude of 0 is not defined. Argument of 0 is equal to not defined. Its magnitude is although 0, that is magnitude of complex number 0 is 0, but is principal argument or argument is not defined. Find the modulus argument and principal argument of following complex numbers. So first we need to find modulus, then argument, then principal argument of the following. And in this case, let's say first case, we have modulus of 7 minus 5 iota is equal to under root 7 square plus 5 square, that is under root 49 plus 25, and that is equal to under root of 74, as you can see here. Let's say first calculate the principal argument of the complex number. So amplitude of 7 minus 5 iota, as you can see this is in fourth quadrant, so this is equal to minus tan inverse of minus 5 upon 7, and that is minus tan inverse 5 upon 7. This is the amplitude of this complex number. Now if we talk about the argument of the same complex number 7 minus 5 iota, then what we will write it as? We will write 2k pi plus theta, that is amplitude, and that is minus tan inverse 5 by 7. So here you can observe one thing. If amplitude of a complex number z is theta, then their argument of the same complex number can be written as 2k pi plus theta. So we will remember this point. Let's have second question. This is in first quadrant. So modulus of root 3 plus iota root 2 is equal to under root of root 3 square is 3 plus root 2 square is 2. So this is root 5. And let's talk about the principal argument. Amplitude of root 3 plus iota root 2. Since this lie in first quadrant, so this is tan inverse mod of root 2 upon root 3, and hence tan inverse of root over 2 by 3. And then argument of z is equal to 2k pi plus tan inverse under root 2 by 3. Let's move on this question. First you need to know about 310 degree, and you can observe that this is 360 minus 50. So 310 degree is in fourth quadrant, and in fourth quadrant cos and sec are positive and rest are negative. So you can observe here this is positive and this is negative, so negative into negative, that is positive. So the complex number, this complex number looks like it is in fourth quadrant, but in actual it is in first quadrant. So what we will do is, first we need to calculate the mod of this complex number z, that is under root of 6 cos 6 square cos square 310 degree plus 6 square sine square 310 degree, and that is equal to under root, you can observe here, 6 square into 1, since cos square theta plus sine square theta is 1, so this is 6. You can observe here one thing, that this number is showing the modulus of this complex number here, and we already seen that this complex number lie in first quadrant, so amplitude of z will be calculated as tan inverse mod sine 310 degree upon cos 310 degree, and that is tan inverse, and this is tan 310, that is tan 360 minus 50 degree, and even we can have this as, we will write it as, that is equal to tan inverse tan 50 degree whole mod, and 50 degree is written as tan inverse tan 50 degree is written as 5 pi upon 18, as we know that pi is equivalent to 180 degree, is equal to 180 degree in radian, so 1 degree is equal to pi upon 180, hence 50 degree is equal to pi upon 180 into 50. So you will cancel this out and you will get 50 degree is equal to 5 pi by 18. So tan inverse tan 5 pi by 18 is equal to 5 pi by 18. 5 pi by 18 is the principal argument of this complex number. Let's move on this. This is positive, but this is negative. So the complex number lies in third quadrant, and you can observe here mod of z is equal to 2 in this case. As we know, mod of z is equal to under root of x square plus y square, and this is always greater than equal to 0. So since mod is showing the distance of complex number z from origin, so this will always be greater than equal to 0. If you calculate mod z in this case, you will get it 2. And since this lie in third quadrant, so amplitude of this complex number z will be calculated as minus of pi minus tan inverse mod, that is sine 30 degree upon cos 30 degree, and we haven't count the negative sign here since it will cancel out. So this is minus times pi minus tan inverse, and this is equal to tan 30, that is 1 upon root 3. Tan 30 is 1 upon root 3, and this is minus pi by 6. Pi by 6 is the tan inverse 1 upon root 3. So you can again observe this is 5 pi by 6, so this is minus 5 pi by 6. So minus 5 pi by 6 is the amplitude for this complex number, and principal argument is the minus 5 pi by 6. So argument of z is equal to 2k pi minus 5 pi by 6. Let's talk about this complex number, that is z is equal to 2 plus I upon 4 iota plus, you can see this is 1 minus 1 why minus 1, this is I square is minus 1 plus 2 iota, so you will cancel this out. This is 2 plus iota upon 6 iota, so z is equal to 2 plus iota upon 6 iota. If we multiply by I on numerator denominator both, then you will observe here, that is minus 1 I square minus 1 plus 2 iota upon minus 6. Why minus 6? Since I square is minus 1. So this is equal to 1 upon 6 minus iota by 3. So mod of z is equal to mod of minus 1 plus 2 iota upon minus 6, and that is equal to 1 by 6 times under root 1 square plus 2 square. So hence this is equal to under root 5 by 6. That is the modulus of complex number z. Now you can see that this is in fourth quadrant. So amplitude of z is calculated as minus of tan inverse mod 1 upon 3, that is minus 1 upon 3 upon 1 by 6, and that is equal to minus tan inverse 2. So amplitude of z is minus tan inverse 2, and hence argument of this complex number is equal to 2k pi minus tan inverse 2, and k belongs to integer. So I hope in this example you have learned about modulus argument and principal argument in various situations. Here is another question. If 1 plus 2i upon 2 plus I equal to r cos theta plus iota sin theta, then there are four options. You need to find the correct option. Let's first write z is equal to 1 plus 2 iota upon 2 plus iota, and if we multiply it by its conjugate 2 minus iota, then you will see that this is 2 into 1, that is 2, and minus 2i square, that is again plus 2, and here we have 2 into 2, that is 4i minus I upon z plus z into z bar is the mod of z square, that is 2 square plus 1 square. Earlier we have learned about this, that is 4 plus 3 iota by 5. So that is the complex number z. Now if we talk about mod of z, that is mod of 4 plus 3 iota upon mod of 5, that is 5, and you will observe that that is 1, and this is also the r, as you can observe here. If this is mod z, if this is z, then you will observe that this is r. So r is equal to 1. So you can observe here a and c are showing r as equal to 1. Now next we need to move on the argument theta. So argument of z, that is theta, can be written as tan inverse mod of, this is in first quadrant, so 3 by 5 upon 4 by 5, and you can see that is tan inverse 3 by 4, and so you can see that A is the correct option in this question. Here is question number 4, and these are their options. So let's solve this question. You can solve your own as well. We need to find the relation between x and y, and then we need to find the k. So you can observe here this is very huge number, and before proceeding, first of all we need to observe this complex number. So what you can have is 3 upon 2 plus root 3 by 2 iota to the power 100 can be written as, you can take root 3 by 2 as common, so root 3 by 2 to the power 100, and the remaining must be root 3 plus iota to the power 100, and this is equal to 3 to the power 50 upon 2 to the power 100, and root 3 plus iota to the power 100. So first of all we need to learn about the pattern of this power. So if we have root 3 plus iota square, then you will observe here that is root 3 square is 3 plus I square, that is minus 1, plus 2 into AB, that is 2 root 3 iota. So this is gonna be 2 plus 2 root 3 iota, and it is not gonna help us anymore. Now let's talk about root 3 plus iota to the power 3. We are finding the pattern to get the value of this huge power. So if we think of q, then this is equal to aq plus bq, that is q of root 3, that is 3 root 3 AQ, plus BQ is IQ is minus I, plus 3AB, that is 3 root 3 I, 3AB times root 3 plus I. This is a formula of A plus B whole cube, that is 3 root 3 minus I, and this is 3 root 3 I into root 3, that is 9I, and if you multiply by I here, then you will get I square, that is minus 3 root 3. So this is gonna cancel out, you will get 8I. Wow, here you get a first result you can observe here, that is root 3 plus I whole cube is equal to 8I, that we need to remember here. So this will resolve our question. So our question is 3 to the power 49 times x plus iota y. Let's arrange some values, that is we need not to have these values. So what we have observed here at the moment, that is root 3 plus iota to the power 3 is equal to 8 iota. Now we will remember this, and our question is 3 to the power 49 x plus iota y, and that is equal to this is equal to 3 to the power 50 upon 2 to the power 100, and we can write root 3 plus iota to the power 99 into root 3 plus iota. So you will cancel this. This is x plus iota y is equal to, if you cancel this you will get 3 alone, and here you are getting 2 to the power 100, and here you can see that this is root 3 plus iota to the power 3 to the power 33. So you will get 8I to the power 33, and this is multiplied by root 3 plus iota. So you will get 3 upon 8 is also 2 to the power 3, and that multiplied by 33, that become 99. So this become 3 by 2, and I to the power 33 is equal to I. Since if you divide it by 4, you will get remainder 1. So this is I times root 3 plus iota. Now we have a relation x plus iota y as x plus iota y is equal to 3 by 2 times I into I, that is minus 1, and I into root 3, that is plus iota root 3. So you can observe one thing, that is x upon y, that is k, x upon y, that is k, is equal to, if you have x at numerator, and this will be in both numerator and denominator, so this will get cancelled out, and hence that is minus 1 upon root 3. So k is equal to minus 1 upon root 3, hence D is the correct answer in this case. Here we have exercise related to the theory that we have done in this video lecture. And there are 5 questions and their corresponding answer. Solve them to build a concept within you.